Just some announcements. So next week we only have one lecture that will be on Friday at this time, and that will be online. That will be by Anand Dev. Because Friday at this time, and then we'll give one more lecture Wednesday the week after that. And we will resume in this class 2 weeks from now. Okay, so that part is clear. Okay, good. So agenda for today is I'll just quickly state the Fubini's theorem. Proof is nicely given in Shriayev's book, not so much in David Williams, but it's just, now you know the basic steps. So it's kind of same steps just used over and over again. So you can see that on your own time. And today we'll then move on to conditional expectations. So that's the plan. Huh? So Fubini's theorem, I'll just give you a setup for it. So you have a flavor of what's involved. So you start with, okay, you have a space omega 1 cross omega 2. Right? So you take a product space, call this omega. Then you take a sigma algebra F, which is a product of two sigma algebras. So F1 and F2 are sigma algebras on omega 1 and omega 2. And this just means that, I take a Borel set from here, I take a Borel set from there, take their cross product. So this is a smaller sigma algebra which contains all such cross products. Right, as you'd expect it to be. And then, I'll assume that there's a measure here, mu1 cross mu2. So this is my space now. Omega, mu1, I guess. So this is a measure on, on F, and A cross B, mu1 A times mu1 B. For A in F1 and B in F2. So you look at a measure which agrees with these sets A and B belonging to F1 and F2, and this will have a unique extension, and that's your measure mu1 cross on the product space. Okay. Right. So this is all well defined. And then we'll assume that X is a random variable in this space. Right? And we'll assume that, okay, omega is mu1 cross mu2. So this is loose notation. People will express this in variety of ways. You can also write mu1 cross mu2 into d omega 1. But we mean the same thing. So I'll assume that this is it's a well-defined quantity, right? The joint space. So I'll assume that this is finite. And then the Fubini theorem is going to say, if I remember correctly, I'm going to look at these quantities. X, omega 1, omega 2, and d mu1 omega 1. So my omega 2 is fixed here. Then integrate this over omega 2. Right? So now this is a function of omega 2. So this is a function of omega 2, right? So it's a measurable function of omega 2. The integration is omega 1 over omega 1. Yeah. So it's a measurable function of omega 2 that has to be shown. And the way you show this is you take indicators here and then you build up things. Sometimes you use aggregation of sets principle. Sometimes you use the fact that you have pi system and it's a measure the weight pi system. They agree on the overall sigma algebra. So just with these three tools you can do these things. Right? So this is going to be a function of omega 1, measurable function, so its integral exists. One can define its integral. Right? Similarly, I can go to omega 2. So this is a function of omega 1 now, and again it's a measurable function of omega 1. Right? And then one can show that if I integrate this function over omega 1, Sorry, I think there was some confusion. I guess I should call this omega 1. So what we are saying both for Anirban and so on is that, what I'll do is, so suppose I'm given a space omega 1, f1, p1, mu1, and omega 2, f2, p2, mu2. So I construct a product space omega, which is omega 1 cross omega 2, and sigma algebra f1, I just call it f1 cross f2. I don't know what to call that. Do you know what to call it? Huh? Cross is fine. There's some F1 cross F2. But the point here is that this contains all the sets A and B, so that A is in F1, B is in F2, their product, and smaller sigma algebra which contains all this.
Then maybe the sigma of F1 cross F2.
Yeah, so sigma of F1 cross F2. Okay. F1 cross F2 is shorter. And then you have a measure on this, a product measure mu1 cross mu2, such that on A cross B it's equal to mu1A times mu1B. And then this will uniquely extend to F1 cross F2. So that's my joint product space. On that I have a random variable x omega 1 omega 2, such that this integral on the joint space is finite. So that's given. Okay. Then the point is I can now I can fix omega 2. So when I fix omega 2, I have to argue that x omega 1 omega 2 is a measurable function of omega 1. So that's an argument that needs to be made. But that can be made. So it's a measurable function of omega 1, so then this integral is well defined. Okay. And this integral in turn will be a measurable function of omega 2. So that also needs to be shown. So then these are things which I am not showing. You can, a good place is Shreya. I think many books generally kind of rush through these things, but Shreya does a good job of going step by step. All right. Similarly, here now x omega 1 omega 2. If I fix omega 2, if I fix omega 1, it's a measurable function of omega 2. So this whole thing is a measurable function of omega 1, right? So that's what we have. And then the theorem is along with these things. Because now I can define this integral. It's well defined. And this is equal to omega 1, omega 2, x omega 1, omega 2, d, 2 omega, d, mu1 omega. And these two integrals are equal to what we had earlier, x omega 1 omega 2, x omega, d of mu1. Okay, so that's the theorem, right? And you just kind of build it up. It's true with for the simplest things and for everything else. So is that fine? Shall we move on? Okay, so that's all I was going to say on Fubini's theorem. This is the kind of thing one can do on personal times. That's well spelled out. So with this now I'll move on to, let me just see if I'm missing something. Yeah, no, I think that's all I had here. Okay, now I'll move on to conditional expectations. Right. How much do you know about conditional expectations? So you know in measure theoretic sense how we define them?
Like if I have a sub-sigma algebra which is contained in my given measure space, and I can define it as a random variable which is measurable in that sub-sigma algebra and which satisfies the property that integral of x x over some set belonging to that sigma algebra is equal to integral of that.
So it integrates like x. Shraddha, you know this already? You'll say this, okay. You know this, Ranjan?
No, not much.
No. Malal, have you seen this before somewhere?
No, not in this. Not in the measure theory set.
Sorry?
Not in the measure theory setting.
Not in the.
I mean, not in terms of sigma algebra.
Okay, so let's just do a quick motivation of this. We're just kind of putting the context. So we know what we mean when we write this, like x is equal to x, given y is equal to small y. In elementary probability, we know these things, right? This is right. So this is the condition of the fact that we've seen lambda variable y's value, it takes small y. The probabilities of the state space changes, and we get these probabilities. And now you can talk about E of x given y is equal to small y. And this becomes x of x y is equal to small y. And in elementary probability, that's kind of enough, right? You've seen something, probabilities are modified, part of the expectation change. Like this, this one, yes. And one problem with this you can immediately see, right? One problem with this is simply that what happens when probably the y equal to y is equal to 0. Right? You could say, okay, maybe there's a density function, so I can somehow define a conditional density function. But we are looking at more complicated things than that, more complicated densities that exist. So for example, suppose I have my y is uniform between 0 and 1, and suppose my x is geometrically distributed with parameter y. Right? So probably that x is equal to n, when y is equal to y is equal to. So that y power minus 1 minus 1. So it depends on how you want to look at y. Okay, so this is already kind of complicated object. It doesn't have a density. X and Y don't have a joint density together, right? So you want to come up with a more satisfactory theory. Now, what do? You could have said that, okay, maybe my y is not equal to y, but it's in an interval plus minus.
Expectation of expectation of age.
You can define. I'm just saying you can't use densities to define this thing here. This doesn't have a joint density, for example. So generally, you need a more satisfactory theory to handle the event which has 0 probability. Right. So how does one do that? Now, if you're Kolmogorov, it just comes immediately to understand. So this all this is sorted out in 1933, but otherwise it needs to be motivated. I mean, in the sense when he put this whole probability in an axiomatic framework in 1933, he also came up with this conditional expectation definition in the generality. It's quite a nice definition. But in any case, what one observes is that with this definition here, you have this property that if I look at y belonging to some set A, then E of x given y is equal to y into probability that y is equal to y. If you look at this quantity here, for any A, this is going to be summation y represent A, summation like this x, x equal to small x, y equal to small y. For all x into. So this is all in a setting where the denominators are positive. And then you observe that you have this identity. this relationship is true. So the way we define conditional expectation, this relationship is true. More abstractly, this relationship can be written as E of x given y dp y of set A is equal to integral x dp y belongs to. So what I've done is, the other issue, it's not just the fact that, so this can be thought of as a random variable E of x given y, which on omega where y is equal to small y takes this value. Right, so this guy takes this value. But the point is, in many areas we see later as we do advanced probability that we need this as a function of y. That's very important to us. So we want to see this as a function. So now you realize that to this relationship is captured by this equation here. This elementary probability definition. And you can go back and look at assume x and y are continuous and define this conditional expectation for continuous conditional density. And again, you'll see that the property is going to be true. So then the thought was that use this to define E of x given y. So that's a general idea, but once you go in this direction, the way we are thinking about this, given y, so along with y, we have a sigma algebra y associated with it, right? So it's like conditioned on random variable y, so we have information, and one thinks of information more generally. So natural generalization is let's define E of x given sigma algebra G. So instead of defining E of x given y, we define E of x given sigma algebra G, and that captures things like, okay, you can have E of x given y1, y2, and so on. Right, so this will boil down to a sigma algebra corresponding to these variables, or E of x given event b. We write this as a E of x given sigma algebra, which makes the event b measurable, indicator of the event b measurable. So all of that is captured in this framework. So that's kind of the background way of thinking about this. Now let's come to the definition of conditional expectation. So I'm given a so I'm given the random variable x, which belongs to L1 mu fp, right? I'm given a G, which is a sub-sigma algebra of x. It's a sigma algebra, but it's smaller than that. Let me just make sure I get the terminology right. Then there exists a random variable y such that y is G measurable, right? It's integrable because x is 3 is the main property. Integral y dp over any set A, integral x dp over set A for all A in G. Right. By the way, I should say one thing before you go further here. there's a big jump between the last blackboard and the new blackboard. Between this equation being equal to this equation and this equation being equal to this equation, right? This is on the underlying space omega. This probability measure on the underlying space. Well, that's probabilities are defined on the real line. So you've seen those things, right? That for example, E of x is integral x dv. But when x has a density, then it's also equal to x fx dx. Right? We've seen how to go from here to there. Because again, if this, and this could be true for just any function of x. Because you say to yourself, okay, suppose my h of x is an indicator. Because the way I start is I'm given, along with this, I'm given that, okay, what am I given? Probability of x lying in A is equal to integral f of x dx by x in A. Suppose I'm given this, right? So this is given to me, then E of x will correspond to this. And that's because you say to yourself, okay, suppose this h of x here was indicator function, then by definition this is true. For simple functions, it's true by linearity, and by modal theorem, it's true more generally. So that's what I'm implicitly assuming here as well, that this actually corresponds to this. Okay, so need to be aware of this. So the point is, y is a random variable which is g measurable, but it indicates like x on the sets which belong to g. Okay. Further, if it is y tilde with above properties, then y tilde is equal to y or Roche. So such a y is unique or Roche. Because that's a big point here. So we'll see now what we'll do is we'll prove this in two different ways, existence of y. One is it just follows immediately from Linearity theorem, but it also follows from a projection theorem that we did last time. It's good, because it's good to see these things, I just kind of go through them quickly. But the intuition as to what does this y look like, you can imagine, for example, suppose your f is sigma x. W and Z, right? It's the smallest sigma algebra which makes three random variables measurable. And suppose your G is equal to sigma of W and Z. So then I'm saying my Y is W and Z measurable. So one thing which I have not proven right now, but it can be proven that if Y is W and Z measurable, then it's a Borel function of W and Z. that requires a proof. Yeah. So basically what I'm saying is there's a function, let's just call that function, let's call it h of w and z, so y is equal to h w and z dp over all sets a and g is equal to let me not call it x, let me call this random variable as some function of g, let's call it g of so I have some random variable which is a function of x, y, w as well as z. And now what we are saying is that there exists another random variable which is function just of w and z. So it's a smoother version of this guy. With the property that all the sets A which belong to G, which is sigma of w and z, on those sets, this guy integrates like this G. Right? So this set A is specified, for example, by W lying between 5 and 10 and Z lying between 5 and 10. Okay? Let me just say, suppose the set A is W equal to 5 and Z equal to 5. So then this guy is just a constant here. While W equal to 5 and Z equal to 5, this guy might still depend upon it. So on the set W equal to 5, Z equal to 5, this is not a constant. It still depends on the value x. So it could be, somewhat a noisy function. But this guy here is a constant. Okay, so it's a smoother version with the property that it integrates like this guy on all sets A and G. And it's going to be, this guy is going to be G measurable. That's the most very important. Okay. So it's if you've not seen it before, it's somewhat non-trivial what more you can do with this. It's not just a straightforward generalization of u of x given by it's more interesting than that. But basically, you need to keep in mind that what you've got here is a function of it's measurable with respect to g. So that's the idea. Okay, so now we're going to prove the existence of this guy. So let's just go back. Any questions so far? Okay. Yeah.
The G function is kind of a projection of H.
Okay.
Like saying that A is A in that region.
Right.
So there's no values are fixed. So basically, G, like I'm thinking that H is like getting projected for this.
You're saying, can we think of G as kind of a projection of space? Yeah. So the way to think about this is you have a space of L2 functions, random variables on the space. All the random variables which are F measurable, and we have the second moment is finite. So that's L2F. On that, you have a subspace L2G. All the random variables which are G measurable, and whose second moment is finite. So that's one concrete way of thinking about it.
Then you do like slicing, not projection, but it can be.
Yeah, it's a subspace. It's a subspace. So one is a bigger collection of random variables, then it's a smallest collection of random variables. Otherwise, you can't think of sigma algebras as projections of a larger sigma algebra. I don't know if that notion kind of pans out. Projection
Theoretically not, but
yeah. So it's so I don't know how far one can go with that idea. It's true, it's a subset of that. Yeah. But projection makes sense in Hilbert spaces. It's a very well defined. Okay, so one proof is very simple. We just define u of A is equal to integral x dp for all a in G. And let's keep x to be x plus, non-negative. We can do this separately for x minus. Okay. So now you can, can somebody complete the argument for me from here? I want to define y plus.
It would be a measure on the sigma algebra G, which is continuous with respect to P.
Yeah, you know something. You got it. That's correct. That's correct. Anybody else? No, you're right. So what Agnew is saying is that okay, P of A equal to 0 means that this side is equal to 0. That implies nu of A is equal to 0. And hence we use Vedanta derivative. And this is true for all A in this implies that there exists, I guess let's call it y, which is G measurable, so that mu of A is equal to y. Right. So from here we conclude that okay, nu of A equal to y dp, mu of A is also equal to x dp for all A in G. So we're done. So this just follows from Vedanta theorem. More interesting result is if you use a projection theorem. So we do what Sunandan was suggesting. We look at so I'm going to so I can do this by the way for x plus, then I can do this for x minus, and then my y just becomes difference of between y plus and y minus. So that's okay. So the other way to do this is through a projection theorem. So we look at L2 mu of p, that's our space here. On that we have a subspace, which is your L2 mu GP. Okay. I'm going to assume now, for now I'll assume my x is in, so my x belongs to this space. So my x belongs here. So then I'm guaranteed a y. Because you know my L2 mu GP is complete. It's a subspace and it's complete because for whatever we proved, you can use exactly the same arguments. This will be complete. So then there'll be a y, so that E of x minus y into z is equal to 0. So E of x minus y into z is equal to 0 for all z in L2. Just very quickly, we're trying to prove the existence of conditional expectation. You probably know this, but one is just straightforward from Vedanta theorem. The new A is defined to be xdp, then you know PA equal to 0 implies new A equal to 0, so there exists a y, which is G measured. Second is now we're looking at the space L2 mu of p. Our x is in that space, so we're assuming a second moment exists. And then we look at another subspace of L2 mu of p, that's L2 mu GP. Right? It's a closed subspace. So there will be a y here from what we discussed last time. So that E of x minus y into z is equal to 0 for all z in this space. So in particular, I can take z to be indicator of for A in, and then I'm done, right? This condition that I had, you've not seen it enough. It's instructive to know. So what I get then is E of x I A is equal to E of y I A for all A in G, and this is just another way of writing x dp over A, and this is y dp over A. Okay, right? So my projection theorem told me that such a y exists, which is G measurable, right? So very nice way to think about conditional expectation. This is L2 mu GP. So you want to find the random variable which is closest to X, right? And that's the conditional expectation. A neat kind of a geometric interpretation, right? Okay. What else do I want to say here? Yeah. So I'll extend this to, I guess we should extend this to X also, to L1 also. We've just done this to L2. So we need some properties to extend it to L1. We need to argue that, okay, if X is non-negative, then E of X given G must also be non-negative. Right? How do we prove this?
The expression of E of X by G over any G measurable set is non-negative.
Right. Yeah.
So now if it was the case that E of X.
Yeah.
So now you can take A to be the set of all the set the G measurable sets such that E of X given G is less than set.
Right. Let's take A to B. So this is fine, right? This is equal to X dp integral. X is non-negative, so that integral is non-negative. So let's say A to B or omega so that E of X given G is less than 0. Right? Yeah. An easier way to now move things is, just let's go by contradiction. So if you tell me if this probability was greater than 0, right? That's what we want to say, that it cannot be greater than 0, right? So suppose it's greater than 0. This would imply that there exists n so that it's greater than 0 for some n, because this event is just a union of these events, right? So some n has to be, some set has to be positive. Right? So now let's look at this. Let's call this set as R An, and let's look at this quantity at An. Then we know that this quantity is going to be less than or equal to minus 1 by n into probability of n, right? And it's also greater than or equal to 0. So the only way that can happen is P of n is equal to 0. Okay. So then you have quantity, because we started by postulating that P of this thing was positive and this thing was positive, but this thing cannot be positive as this thing. So is that clear? I look here today. Is that clear? Okay, we should also, now we've got this. This will make our proof so again, these are kind of things you have to again see. If you do it by yourself, you come up with rough arguments, but it'll take much longer to come with precise arguments. But now we want to argue that, okay, so suppose I take, suppose my x in L2, my x in L1, and I want to argue that there exists a y so that x dp is equal to y dp for all a and y is n. So I want to argue the existence of such a y now with my x in L1. So what I do is I look at, I guess, xn, which is just x into indicator that x is less than or equal to n. So I truncate. Okay, once I've truncated this, Then it's in L1, then it's in L2, the truncated variable. So I get a yn. So I get integral xn dp in A is equal to integral yn dp in A. Further, I know that this xn is increasing to x. And I also know that yn is, this yn is increasing to y. To y is increasing. Let's call y equal to then soup and goes to infinity yn. Because this is well defined. And I know y is increasing because of what we just did.
Yeah.
Right? Yeah. It's exactly because xn minus 1 is non-negative. So the difference of the conditional expectation E of xn given g minus E of xn minus 1 given g is also non-negative. That was important. All of these are almost sure, so you have to take the intersection of all these almost sure sets. The countable intersection of sets of probability 1 is also a set of probability 1. So that's very useful. This breaks down when you go to continuous time. But then you do uncountable intersections. If you have continuum of times and all that. That comes up with its own set of problems. So that's a much harder problem. So we'll do some continuous time math and we do running motion. So we'll see this thing there. All right. Yeah, so now we have this. So then, so I want to say that such a y exists. My x is in L1. Can somebody help me complete the argument?
And so integration of y dp over g is equals to integration of y dp over
Oh, x over.
x over.
Because, and why is that? Modal conversion, right? Xn is increasing to x, so xn into indicator A is increasing to x into indicator A. So by modal conversion, this is going to increase to indicator x dp over A. This is going to increase to y dp over A. Right? Y is G measurable because it's a lim sup of all the y's which are G measurable. Right? So now we have that candidate. So y is my candidate. My y is my answer. Okay. Right? But you have to realize that each yn we have defined almost only one set. So we have to intersect all those sets. On the intersection, yn is increasing. Right? When you have a set where yn minus 1 and minus 1 is not negative, almost only. You intersect them over all n. But those are, I guess, nuances we don't spend too much time on. Okay, so we have this. We still have to prove that y is unique. So if I give you one y dp, y and y tilde are G measurable. A is in G for all n G. Then why do they have to be equal? This is again a generic thing.
After truncating, they will be
You may not need to go that far.
but L2 this is not right.
Yeah.
For L2.
Oh yeah, I see. Yeah, because we have the already unique. Sure.
Then it's a lim sup of the truncated.
So that would be a complete argument. That would be a correct argument. Yeah. True. Because it's unique there. So it's unique for each y and so that. Another argument which you can just see from here, because we also prove this using rhetorically, is that you suppose that they're not. And you repeat what we just did a few minutes ago. So that means probably that y minus y tilde is greater than 0 and that has positive probability, let's say. Right? So without loss of generality, if they're not equal almost surely, then y minus y tilde is greater than 0 with positive probability.
Integration of x dt over.
Yeah. This would mean that there's some n that y minus y tilde is greater than 1 minus positive probability. Now you take this set to be a k almost. And this is supposed to be equal to 0. And now you get a contradiction. Right? Something which is 0 is also strictly negative. That's what happens. So I show you the step. Again, I'm just outlining something, but these are things which are you'll see, for example, table Williams. Okay. Let me just spell out. So on this set also I have, y minus y tilde dp over this set a is equal to 0, because this is true. But on the other hand, I also have this point p is greater than or equal to 1 by n into probability that y minus y tilde is greater than 1 by n. So that suggests that this cannot be positive. This has to be 0. So this is true. Which contradicts the fact that we assume it's just positive. So hence y and y tilde. So this will tell you that okay, so y must be less than or equal to y tilde. Y cannot be greater than or equal to y tilde. Y cannot be strictly greater than y tilde with positive probability. So y must be less than or equal to y tilde almost surely. By symmetry, you also get that y tilde must be less than or equal to y almost surely. Y is equal to y. Y tilde is equal to y. Right? So now we'll do some properties of conditional expectation. I go through them. This you've seen this thing here and there, but it's, some of these things are good to see again and again. So what is the expected value of E of x given G? E of x, right? So I'm going to use the notation E of x given G, although these things are defined only up to a set of full measures, right? This means any version. So these are called versions. Two random variables which are equal almost surely, they say they are versions of each other. So any version of this will suffice. And this is E of x. And why is that the case? How do we prove this?
The probability x by the equivalent set is equals to probability.
Yeah. Well, we have this, right? We already have that E of x given G dp. Just take a to be omega.
Yes.
Yeah. Right? Okay, right. So suppose x is G measurable. Then what can we say about E of x given G? Equal to x, right?
X, surely.
Because now with x it satisfies all the properties that we need to satisfy. It also fits in with our intuition that given G we know x. This condition. So the way to think about this and this, we got a very nice intuition for this condition from the the Hilbert space, that it's our best approximation for x given that we are lying in G, right? So when x itself lies in G, then of course the best approximation is x itself. But yeah, this is a good thing to keep in mind that this is really a best approximation for the random variable in the space of all G measurable random variables. Okay. Yeah. So linearity is as a, if you're seeing it for the first time, it is a nice proof. So expected value a1 is equal to ax plus by. All of this I'm assuming x and y are in L1. Given G, and x and y are measurable. So why is this true?
The right hand side satisfies both those integral equality. Equation ax plus by dt is equals to a integration dt plus b integration by dt.
So just say again, just
So integration ax plus by dt over a G measurable state is a integration is
see, basically we need a new variable which is G measurable and which integrates like ax plus by.
and which is equals to a integration x dt plus b integration by dt.
So I'll just complete the output. So we're looking for a random variable Z, where Z has to be G measurable. That's what we're looking for. Right? For all n, this has to be G. That's the requirement. Now what Shirato is saying is that this by linearity is just a of x dp plus b of y dp. And hence, what do we say?
A integration e x given G dp plus b integration y
If this, we know that this thing exists, this random variable exists. By linearity of expectations. So this becomes a candidate for Z, but this is G measurable, right? And we know that this can, this is unique almost surely. So this is a version of conditional expectation. So indeed, we get that relationship that this is equal to this almost surely. Okay, that's clear. So we get linearity. Okay. So monotone convergence theorem, conditional monotone convergence theorem. What will be the statement?
if one is to if
So what would be a good statement for conditional monotone convergence theorem? Any guesses? The monotone convergence theorem was that if xn is non-negative, then it increases to x, then e of xn increases to e of x. So what's the natural thing to in the setup that we are in right now?
e of x and given G this is 3 of x.
We again given the same setup and we want to argue that e of xn given g increases to e of x given g. And we've kind of done this already. Because E of xn given G is dp is equal to xn dp over A, right? This is true. Xn is increasing, so E of xn given G is also increasing. So again, I'll divide a lim sup of this guy, right? And then by monotone convergence theorem, I'll argue that the lim sup of this guy, let's call that then integral y dp A is equal to integral x dp A. And I get this for all A. So indeed, y is the conditional expectation of x. Right? This is exactly equal to lim sup, which is what we want to do. You know, we always know that this exists, but this is convergent to that. Right? Okay, so monotone convergence was followed. Let's prove Fatou's lemma. Conditional Fatou's. So what's the statement here?
If it is equals to 0 almost still. Integration AB of n given G.
So let me just write the old Fatou's lemma. So old Fatou's lemma was
If n greater than equal to 0 almost.
xn, right?
So in expectation of limit of xn is less than equal to limit of xn.
That's Fatou's lemma, right? So now we want to say what?
Expectation of limit of xn given to 0.
See, this is our random variable, and this is less than equal to. Right? So this is also going to be. Yeah, I'm just trying to remember the proof of this. Good. In the morning, I should go. Okay, so we know that, so let's define, I guess we define yn to be infimo n getting equal to n xn. Right? So then yn is equal to
Let's get xn.
xn. Sure. And let's define E of yn given G is equal to E of infimo xn. Right? Okay. Now this is going to increase with n. So we can use monotone convergence theorem. Right. So this limit of as n goes to infinity, E of yn given G is equal to right? This is what we want to get a handle on. So now we know it's equal to this guy. And now you realize that okay, this E of yn given G is less than equal to E of xm given G. So all m get into n. So now when you take a limit of this, you take a limit on both sides, the inequality persists. This inequality is equal to this guy, and that's going to be So we get answer. So monotone convergence theorem helps us basically. Okay. All right, so now we do conditional dominating convergence theorem. So again, the usual DCT is that xn is less than or equal to y for all n. E of y is integrable, and xn converges to x implies E of xn converges to E of x. Right? So what will be the conditional version of this?
Given G.
Yeah.
H2 of X given G.
Yeah.
Given that X and given G of X.
So, just given this. Okay, so we are given this condition, this condition, this condition. Now, rather than asking for this, we ask for something stronger. We're saying this is true. And for all G, including trivial algebra. So, trivial sigma algebra is G equal to omega and phi, right? And then you can see that E of xn given G is what?
E of X.
This is equal to E of xn. So if this is true, then you recover this. Right? So it's strengthening of dominant convergence theorem, strictly. I think everything we've done is basically strengthening of these theorems. So this, let me tell you what the proof is. If you don't know it already, it's not something one can easily guess to come to. You have a guess? Well, if you are kind of familiar with these things, then you say, okay, it's not difficult, no, it's good. It just follows. And it follows basically because I can use y minus xn and y plus xn. And I can apply for two dimensions most of these things. And then I'm done. So that's something for you to learn, I guess, that one can always do these things. So starting at limit of I guess I'm looking at. I mean, this I could have done when I was proving domain conditional from Hatu's level. But now I'm doing conditional, so I just do this given G. You just show this, right? So this I know is just going to be y minus x, right? Yeah, how do I know this? Well, I mean, this is a random variable inside, so that is goes here. This is going to be E of y minus x given G. And that's less than equal to I minus lim soup. So I get that lim soup of xn given G less than equal to x given G. Now when I go in the other direction, I have plus here and plus here, right? I have plus here and plus here. Both of these are everything is non-negative. Y plus x. So we apply for this, right? So then I get plus here and I get limit here. If you see it, we're going to do. Is that okay? Okay, so let's do maybe conditional Jensen's. So everything I'm doing right now is from David Williams. And that's a great book for this conditional expectations and for market. Hard to find any book that matches up to this. So what will be conditional Jensen's? We have a convex function. Right, so Jensen's was okay. Phi of E of x E of C of x, right? And what you maybe really need is that, okay, phi of, what did we need? I guess all we need for this really is this. This could be infinity, but that's fine. Right? So what will be the conditional Jensen right now? Right. I'll use some this kind of some standard results from convex theory without proving them. So C of x, Phi of x, Phi of x equal to swoop and an x plus bn. So there exists an bn. So I can get these countable lines, right? So that the supremum at any x gives me phi of x. But the point, of course, is that I have this convex curve. So I look at all possible lines which lie completely below it. I'll collect all those lines. At every x, I take a supremum across those lines. That gives me C of x. Right? But for any collection of such lines, I can extract those lines which an and bn are rational numbers. So I get now a countable collection. And this property is still true. There I just said, if I give you a convex function, I look at all lines ax plus b, which are completely dominated by the convex function. I collect all of them. And then supremum across those a's and b's will give me equal to C of x. If not, then you get one more line by separating hyperplanes. And if it's anywhere it's lower, so that gets a contradiction. So supremum will get you there. And once I have that collection, I can just look at a and b which are rationals from that collection, a subset of that, and that's a countable subset.
Actually, these are convex functions and treated as a supremum.
That's why I said yeah. But I'm just giving a proof in some sense for that. Yeah. And the proof just follows from the fact that this is a convex set. The epigraph of convex function, convex set. So you can use separate graph of it. So we got this now, right? So now what do? We look at okay. What do you want to show? Phi of random variable x is greater than or equal to a n for any such a and bn x omega plus bn. Right. F of x omega, I can call it here. So everything we do earlier, now we're doing slightly more omega by omega lambda. In a sense, now we take conditional expectation, earlier we were taking expectation. So now we take conditional expectation, we get and now we just take a shoe from that side, right? And that's exactly equal to phi of the x. Okay. Now it was so Malhar, Daksh, any questions? Who's in this dead my? Oh, Shantanu, hi. Shantanu, any questions?
No, sir.
Okay. If you can, just keep your video on, but I guess your bandwidth is poor. That's fine.
Oh,
But it looks like next time we meet, which will be, I guess, now we'll meet 2 weeks from now on Friday, right? We'll meet, otherwise we'll meet next week, next Friday we'll meet online. And Wednesday after that we'll meet online. So when we meet here, we don't, I mean, should we record the lecture at all or all of you will be here, right? At that time.
Yeah.
No, but I guess the question to all of you is, do you still want to have the lecture recorded? Watch later the
No, I
response.
think Shantanu will not get them because you will come here for game test or something.
Oh, Shantanu, so will you be here 2 weeks from now or no?
no, sir.
Oh, you will not be. Okay, so then that settles it.
Okay.
So we'll have this recording for you. Okay. Yeah, okay. Much as I hate to record myself, but I guess if I'm a student, it's good to have these records. Sometimes just want to go through that. But there's nothing worse than seeing yourself in a video. It's very embarrassing. You just have a way different image of yourself otherwise. Okay, so let's do tower property. Now we are given, we have mu fp. So all of this you'll see, everything you're doing right now just comes up so naturally in martingale that quite fascinating how this is essential to something so fundamental. Okay, so now we have a sub-sigma algebra G and a sub-sigma algebra H. And the question we ask is, what's the conditional expectation of the conditional expectation? X is always in. Okay, so for anyone who's seeing this for the first time, any guesses? Shantanu, Malhar, any guesses?
Is it
H.
directly x given h?
E of x given h.
Right. You're probably not seeing it for the first time. Okay, how do we show this? So you want, let's just go back to the basics. What do we want? Again, we want a random variable y. Which integrates like e of x given g. On all sets H belonging to my sigma diagram, calligraphic H. Right, so I want a random variable y, which is calligraphic H measurable, and which integrates like E of x given G. Right? Along all these sets H. So that's what I want. That's the definition. And now one just observes, as you probably already have, that is equal to x dp. This we know, right? Because H belongs to calligraphic H, it also belongs to calligraphic G. This we know. And we also know that there exists E of x given H, which integrates like x on sets in calligraphic H. So we know such a thing exists. And that is what we are looking for. Like we are looking for a random variable y, which integrates like this guy on all sets H, and indeed E of x given H does that. So this does the job, so this is equal to conditional expectation. So hence this property is true. Right? So this is called the tower property. I guess you're constructing a tower of sigma variables. That's what it means. What would be the case, by the way, if above if we had G subset of H?
This is already expressed.
Yeah.
So the expectation something given each is the expectation.
Yeah. So what will the answer be then? What
E
will
of
the
x.
E of x given G.
E of x will be excellent. Yeah, this is already known to us given this. So it's equal to E of x given G, which is not equal to E of x given G. Okay. Do I have anything else to do? Yeah, taking out, I guess, the other one. That should. So again, suppose my space is mu and p. I have x and z. So x, which is measurable, it's another variable here. Suppose I have z, which is g measurable. And when you just to complete things, all the moments exist. So E of x is finite, E of z is finite, E of x times z is infinity. So we assume all these regularity conditions. Then the question is, what is E of zx given g? So no, they're not independent. They're not independent. All we know is that z is g measurable. Right?
So Z will come.
Z will come. Z will come.
Yes.
So you can take out what you know, because given g, we know z already. Right? So that can just come outside. Okay, let's see how to prove this. So proving is not so straightforward. This one is you use some kind of standard machinery. So we'll assume to begin with that both z and x are non-negative, and we'll prove it for that. I mean, it suffices in the sense if I can show you that, okay, if E of z plus minus x plus minus given g is equal to z of plus minus E of x plus minus given G. And what I mean is Z plus X plus Z plus X minus Z minus all combinations. Right? If I can show this, then this will follow. Because this can be expressed in terms of these things. So hence it suffices to consider Z and X as non-negative. Okay, so I'll assume that from now on, this is clear, right? That if I show all of these things, all four combinations that I've done, then this will follow. Okay. So now I just have to show this when Z and X are both non-negative. And what I do is I just start with Z equal to indicator function of say B, where B is a element of G. Because Z is G measurable. So first I look at all the indicators which belong to my G. So then let's look at this guy here. This is just E Z of X given G dP on some set, let's call it A is equal to integral Z of X dP over set A. True, right? This is how we define things. How do we proceed? Anyone? What I want to show is E of IB into X given G is equal to IB into E of X given G. So how do I proceed there?
So that will be equal to integral of A intersect B X dP.
X, yeah. Right? And that's equal to, so how do we go from here?
Integration EX dP. EX given GT.
Given G dP section D. And that's equal to
Indicator of BX given
A is what I have. Right. So now I get my result that this guy is equal to this guy. And that's what I want to show, right? E of IBX given G. So this guy integrates like IB times X along sets in G. So I've got that here. So now I've got this for indicator functions. So hence I have this for simple functions. And by monotone convergence I have for non-negatives. So I'm done. Okay, that's what that is. Okay, so I mean, there are one or two things which I can also show for conditional expectation, but I'll just do the next time. And then we'll start with margin. We already stepped into that. Okay, so unless there are any other questions, we'll stop the class for now. Okay, guys. So we'll, I guess we'll meet next Friday online. That's our next class. No, stop it.